This work is a joint work with Mark Anderson and Anna Sugel, who's my supervisor. And it is about implicit causality bias and its interaction with explicit cues in language models. Let me start by saying that this is work in progress, and I think it's in a pretty good shape. We're hoping to submit to ACL in a week's time. We submitted to tackle once, and the decision we got was a C, with some fairly positive comments on one side, but also some criticism that the reviewers found was crucial. So in the course of the talk, I will sort of point to the things that we got feedback on and talk a little bit about how we've addressed that. And I would also be very interested in hearing your thoughts at the end about a more general sort of a framing of the work that we think is not the most standard framing for NLP, where mostly it's a matter of chasing benchmarks and SOTA and whatnot. And we don't see this work fitting in that framework necessarily. So I'd be interested to hear your thoughts about our alternative suggestion. Let's start with a little experiment. I want you to think of an ending to this sentence. Don't overthink it. Just take the first thing that comes to mind. If you can, write it down. And let me say that in this scenario, John and Mary, who you'll be hearing a lot about throughout the talk, identify or have as their preferred pronouns he and she respectively. So just think of how you'd like to end this sentence, store it in mind or write it down, and then use the Zoom reaction buttons to tell me whether your choice was a he as a first word continuation, a she, or something else. So if you can, please go for yes for he, no for she, and a raised hand for something else. And I don't actually know. Yes, okay, so I'm seeing one raised hand. It maybe takes a couple of seconds for people to find the reaction buttons. Or maybe I'm not seeing the reactions. That could also be.
I think we don't have reaction buttons for the yes and no, only the raise hand.
Oh, okay, cool. Never mind then. Let's imagine that you had all answered. And my guess would be that a lot of you would have said he. John apologized to Mary because I saw one of you writing something like he was late. That's a very common way people would continue this sentence with a reference back to John. And this is because of what is called the implicit causality bias, which is a semantic property of transitive interpersonal verbs, wherein the cause for an action or change of state that is expressed by the verb is implicitly attributed to either the verb's subject or object. And here are some more examples of what psycholinguists have found to be predominantly subject bias verbs, predominantly object bias verbs, and then some verbs fall in this category of sort of neutral verbs, which don't necessarily attribute a cause to either their subject or object. So in the general case, when psycholinguists ask people to finish this kind of sentences, they might find a pattern like this here for something like apologize. John apologized to Mary because would tend, so this in the study that where I got these numbers, which is Festel 20 and colleagues 2011, they asked 96 people to continue this sentence in an open-end fashion and found that almost 90% chose to continue with he, 3 with she, and 7% with something else. And this implicit causality bias is sort of what allows us to understand narrative in certain cases. So here we see that if we ignore the yellow bits of the sentences for a second, these two sentences are identical. John did something to marry, but the mistake could not be undone. Now, because apologize to is a subject bias verb and console is an object bias verb, we would implicitly assume that whatever mistake was made was committed by John in the first case and by Mary in the second. And this is basically part of how we go about comprehending text and the causal relationships in text. And here are some more examples of ways in which people might continue sentences like this. And it is basically based on these kind of continuations that psycholinguists then might conclude, okay, annoyed tends to be a subject bias verb, reward tends to be an object bias verb, and so on. And it's usually not the case that people would unanimously agree about how to continue these sentences, or basically which referent to refer back to. So the scale is sort of continuous, and on one end we might have something like reward, which is a fairly strongly object biasing verb. On the other, we might have attract, which is a fairly strongly subject biasing verb. And then many other verbs land somewhere in between these two extremes. Now, we cannot do this because I didn't know that you wouldn't have the buttons. But I would have next asked you to tell me how you would choose to complete this sentence, where we have John praised Mary because blank was truly impressed. And my guess
We
is,
can write in the chat if you. I like this interactive talk, so maybe we can write all in the chat. What do you think?
okay, sure, go for it. Just give me a he or a she in the chat.
Yeah, there's a lot of he.
Okay, a lot of he, very cool. This is what I expected. Whoopsie. Sorry, I'm losing my screens. Yes, and this is interesting because in this case, praise, which is an object bias verb, would suggest that the cause should lie with Mary, but the actual context of the sentence points to John, right? So you can always come up with some sort of low probability scenario where John might have praised Mary for her being truly impressed with something or other. But the more likely reading is that John praised Mary because he was the one truly impressed by something Mary did. And I'm showing you this example to say that it doesn't necessarily have to be the case that the implicit cause that lies in the verb semantics aligns with the explicit cause that is in the sentence. And we know as humans that when it happens to be the case that we get these two contradictory signals, we should give priority to the explicit contextual signal. But it isn't the case that that's a sort of one-step process, or put differently, this requires a little bit of extra effort on our side in terms of processing. Psycholinguistic studies have found that when it is the case that these two signals mismatch, or there's a mismatch between them, that leads to delays in self-paced reading times, in eye tracking perturbations during reading, in an electrophysiological response of type N600, and in slower responses in pronoun resolution. So humans would be able to say, to give the right answer, as you just did, that he should be the right pronoun in the sentence I showed you, but it would take like an extra millisecond or something for them to do that compared to a scenario where the two signals align. Okay, I've told you about implicit causality bias. I wanted to get that background right out of the way because I also thought it would be fun to start with these experiments. And here's how the rest of the talk will go. I will discuss why we think that implicit causality bias is relevant to NLP. I will talk about some practical considerations for the study of implicit causality bias in NLP. Then I'll cover some theoretical considerations in the same respect. And then I will describe two research questions that we address, what we find, and finally, what the implications of our findings are for future work. A really cool paper came out last year by Alison Ettinger called What Bird Is Not? Lessons from a New Suite of Psycholinguistic Diagnostics for Language Models. And this paper posits this hypothesis that, or rather they go and test bird or phenomena that show divergences between Cloze and N400 profiles. And to translate that into a more accessible language, they show divergences between the initial response a person has, the sort of immediate brain response they have to a stimulus, and their final answer to whatever task they have been given. So in the case of the mini experiment that we just did, where I asked you whether you would go for he or she, the implicit causality of the verb might have immediately pushed you towards a she, but that would have been so brief and immediate that you wouldn't even realize it. And then the final answer you gave me was he, because you realize what the full context means. Right, so they say that they test bird on phenomena that show this kind of divergence because they expect that these phenomena should present particularly challenging prediction tasks, potentially tripping up models that fail to use the full set of available information. So they're basically saying we expect that the models will get this immediate signal from their lexical semantics, and they wouldn't really bother with integrating the full context in order to arrive at the correct answer. And this relates to topics like that thinking fast and slow framework, for example, where that metaphor from Daniel Kahneman has been used to describe how models are still on the thinking fast stage of human processing, but they don't really arrive at the slower, more deliberate, and more multi-step kind of processing that we're also able to do. And here is how that hypothesis can be formulated in a more succinct way. Basically, the hypothesis of Ettinger that we also explore here is that latency in human processing translates into errors in model processing. And in our case, that more specifically transforms into latency in human processing of incongruent causality signals, incongruent meaning mismatching, translates into errors in model processing of coreference chains. And here is how we operationalize this hypothesis, so to say, with two research questions that we address in turn. The first one being, is a model aware of implicit causality bias? And that is basically the question that psycholinguistics have studied by performing the first experiment that we did, where you show the participant an open-end sentence and you ask them to continue it as they find most appropriate. And this question is sort of a prerequisite for the second, more critical question, because if we find that models are not aware of implicit causality bias to begin with, then there's no need or reason to expect that this bias would lead to some errors when it's incongruent with explicit cues. But then that is our second question. Does IC bias incongruent with the explicit cues lead to errors in coreference resolution? And that is basically the second experiment we did, where we want to know whether filling in the blank in John apologized to Mary because blank felt offended, for example, if models would struggle more in choosing the appropriate word for this blank when the two signals are incongruent compared to when they are congruent. Okay, and you might be able to immediately see that these two tasks in the yellow rectangles basically reduce to a next word prediction task and the close task. And since we have two types of language models pretty commonly used in NLP today, unidirectional and bidirectional models, it's also easy to see that the unidirectional models would be very easily fitted to the next word prediction task, and the bidirectional models very easily fitted to the close task. But it's a little bit trickier to figure out how to test bidirectional models on the first task and unidirectional models on the second. And this is where the like a lot of our work went into. This was actually a kind of fun puzzle to solve. And I hope you'll find our solutions reasonable. So here's how a next word prediction task would be solved with a unidirectional encoder. Pretty straightforward. We feed our tokens one at a time. We arrive at a state from which we can then extract the probability distribution over the next token. And we can then compare the probability assigned to he to the probability assigned to she, and be able to say something like, the model prefers to see the pronoun he in this context or the pronoun she. In this case, in the example, that would be he, because he has a higher probability. In similar terms, it's straightforward to solve the close task with a bidirectional encoder, where we have the full sentence with just one token missing, replace that token with a mask tag, and we then, from the state for that tag, induce a probability distribution that tells us whether the model prefers to see pronoun he or pronoun she in this context. Now let's see how we would go about next word prediction with a bidirectional encoder. The problem with the next word prediction task is that we're missing part of the sentence, not just the token we're interested in, but also everything that comes after it. But bidirectional encoders expect to see full utterances. So if we were to do something like this, where we just query the model with a partial sentence and we look at the probability for the mask token, we find that models mostly predict a full stop. And this is understandable because, yeah, on one side, a full stop is not something that usually comes after the word because, but on the other side, a full stop is something that predominantly comes at the end of the training sequences a bidirectional model might have seen at training time. So this is what we get. And that's obviously not satisfactory. So we considered another option where we mask out the full potential ending. So in this case, the 3 blue mask tokens might correspond to something like felt offended, or the subtokens of that sequence. And we could then look at the probability for the first mask token, the one that's in the position of the pronoun that we're interested in. But there's one problem with this, and it's the fact that many bidirectional encoders have not been trained to see multiple mask tokens in an input sequence. And the ones that have are usually trained in such a way that these multiple mask tokens correspond to the subtokens of a single word. So while this formulation of the task could yield something more meaningful, we're still not convinced that we would really be testing the models in a way that makes sense for them. So here's what we arrived at. John apologized to Mary because mask had no honey. If you're wondering what honey is, honey means nothing. It's a made-up word. And this is basically our solution to the problem. We came up with a way to generate endings that follow, to the best extent possible, English syntax and phonology, but are meaningless. Here's how we generate these meaningless or nonce endings.
Wait, Yova, I have
Yes.
a question. So
Yes.
instead of, if I understood correctly, you kind of looking at the top one of the model prediction, but alternatively, you could also just look. So like if you want to check the relationship between these two, so you could check if he, for example, is given a higher probability than she, or John over Mary. Is this an option you thought about?
So we didn't look at the top one. We did look at the probability that was assigned to he, and we did look at the probability that was assigned to she. So we just compared these two things.
So then what's the what's the difference between using just like a one mask token at the end, or a few, or this approach?
The difference is that if you go for the option where you just end the sentence at the mask token and try to predict something for that, and the model gives you a probability of 98% for a full stop, it's not really meaningful to then go and say, oh, well, he has a 0.007 probability and she has a 0.003 probability. Because I think there is some work that shows that after a certain cutoff in terms of probability, the comparison between words becomes meaningless. So we definitely wanted to make sure that whatever testing paradigm we use will result in he and she being ranked as more or less the two top candidates. And this is what we actually find, because in the example, I put artificial numbers next to these tokens, but in practice, we find that something like 90% of the time, one of these tokens is ranked in the top two positions by the models. And this is the case for the paradigm that we used, but not for some of the others we considered.
All right, thanks.
Yeah. Okay, so here we are looking at how nonce endings are generated. We started off from a data set by Carnum and colleagues from 1996, which was also used for the study of implicit causality and its interaction with explicit cues. And I will talk about it more later on. But for now, all you need to know is that it contains these kind of sentences like John rewarded Mary because she had done well. Basically, it contains examples like the ones I have been giving you throughout this talk. And so what we did was we scraped a bunch of different endings from this data set, from sentences where the two signals were congruent. And we transformed these endings into this kind of template where we keep only the stop words and any open class words are replaced with a placeholder. And in cases where the first word was not a stop word, we used this special status placeholder because we knew that that position would always be occupied by a verb in the past tense, which is just how that data was designed. We then obtained two lists of nonce words from different studies. One containing words that were designed to resemble verbs, and another containing words that were designed to resemble any open class word. And both of these were for English specifically. And we use these words to basically fill in the placeholders dynamically, such that we might from head placeholder obtain something like head, bairn, among. Which I know sounds like nonsense, but the whole premise of the studies that use these nonce words is that these words should resemble valid English strings. And so we believe that by designing endings to the sentences in this way, we're basically telling a bidirectional encoder, here's a valid looking sentence. You're not going to be able to understand what the second part of the sentence means, because in reality it doesn't mean anything, but at least you should be happy that you're seeing input of the format that you've been seeing at training time. And here are some more examples of the different strings that were generated with this method. Right, so back to how we now do next word prediction with a bidirectional encoder is that every time when we want to ask the model, how would you continue the sentence, John apologized to Mary because mask, we basically call this module that generates a nonce ending for us. And this is how we present the input to the model. Okay, and the last thing we need to figure out is how to do Cloze task with a unidirectional encoder. Now, the problem with a unidirectional encoder is that it isn't designed to take in future context. It only operates conditioned on a past context. So what we did here instead was we used a unidirectional encoder as a language scorer instead of a language model per se. So we presented the model with these two strings, each containing the alternative pronouns that we're interested in, and we obtained a probability for each as the average probability the model assigns to the tokens in the string. Right. And one last note on this part of the experimental design is that in the course of this work, the Electra paper became better known, or like we became aware of it. Electra is a discriminative language encoder. Since then, another one has come up called Electron, I believe, or Electric, I don't know. But basically, these models have a slightly different structure than the generative models that I've talked about so far and that have been widely used in the past. And we thought it would be nice to include this type of models in our study as well. So for the sake of making sure that we're all on the same page, I'll just briefly say what a discriminative language encoder is. It's a language encoder that has been trained in this two-player setup where a generative masked language model, so a standard bidirectional model, is first trained on input of the standard format with some masked tokens. And then it is used to generate some made up or like basically replacement words for the original input string. So we start from the chef cooked the meal. We mask out some tokens. We train this generator, which then generates some alternatives for the first and third token, such that the string now becomes the chef ate the meal. And the discriminator, which is the actual component that will later be used as a language encoder, is then trained to recognize which tokens have been replaced and which tokens are the original input tokens. In this case, the replaced token is 8. This is how they operate. So they basically, unlike a generative model, which computes a probability over a vocabulary, these models compute the probability over two labels, original and replaced. And the way we include these models in our study is in very similar terms to how we do the Cloze task with a unidirectional model. Namely, we present the model with the two alternative sentences, one with he, one with she. We compute the probability of class original for each token in the sentence. We average over that, and that basically tells us whether the model shows a preference, so to say, for one version or the other. And the procedure is identical for the Cloze task, the only difference being that instead of the blue text here, which is nonce text, in this case, in the Cloze task, we have a valid string, something like John apologized to Mary because he was late. Right, and here's a summary of all the methods I just described. For unidirectional models, we have these two different approaches for the two tasks, and for bidirectional, generative and discriminative models, we have a single approach that only differs in whether the future context is a non-string in the case of the next word prediction, or a valid meaningful string in the case of the Cloze task. So much for practical considerations. Now moving on to the theoretical considerations. So the choice of pronoun in how models complete the sentence, John apologized to Mary because, can be guided by implicit causality bias, by explicit cues, and these two are really the things that we're interested in. But it could also be guided by things that we don't really care about, like the linear order of the two participants, their gender, or even such subtle things as the choice of proper noun. And these last three things are things that we wanted to make sure we sort of cover to the best way possible in the design of the stimuli, such that we can abstract away from them in the analysis of the results. Here is how we went about figuring out what proper nouns to use. And the reason we thought that's necessary is because of a paper by Mustafa Abdul from last year, who showed that models change their decision about solving the Vinograd schema challenge, for example, based on what proper nouns are included in the stimuli. And so we wanted to find what are the proper nouns that the models would find most expected, like least surprising, and that they most straightforwardly associate with the female and male genders, because this is how we can actually measure this bias by through the agreement between the pronouns and the proper nouns. So what we did was we queried the models with these strings. She is a woman and her name is. He is a man and his name is. For the unidirectional model, and we looked at what are the strings with highest probability to come after this partial sentence. For the bidirectional generative model, we did something very similar. And for Electra, we had to use a two-step process since the model itself cannot generate words from a vocabulary. We used the generator that was trained in the process of training Electra to obtain suggestions basically for this mask token. And then we used Electra itself to validate the suggestions by looking at whether the model predicts the label original or replaced for the different names suggested by the generator. And in this fashion, we obtained 10 female names and 10 male names per model. Here are the actual models that I will talk about. We tested a few more, but I think it suffices to just look at these three because we have GPT-2, a representative of unidirectional generative models, BERT, a representative of bidirectional generative models, and Electra, which is a bidirectional discriminative one. Right, and once we have these 10 names per gender, we then basically did all combinations of male and female names, which gives us 100 variants of a stimulus for apologize to. So we have John apologized to Mary, John apologized to Elizabeth, blah, 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 all the way down to Harry apologized to Rachel. And then, of course, there's no reason to assume that the first, that the subject should be male and the objects should be female. So we also did the two variants in this respect. John apologized to Mary because, and Mary apologized to John because. So then with 100 variants per gender combination and two of these combinations, we have 200 variants for each stimulus. And lastly, a word about the linear order of the participants. English has a fixed word order, so there's not much we can do about changing that around. So it's inevitably going to be the case that the object is going to be closer to the point at which we're making a prediction. The subject is going to be farther away. So this is just something that we should be aware of and take into consideration in the analysis of the results. Right, so now that we've covered a lot of ground in terms of the methodological considerations, let's return to the first research question at the heart of this work, which is a model aware of implicit causality bias? And the way we go about that is we basically replicate the procedure of Festo and colleagues with language models. So they compiled this list of 305 verbs. It's a manually curated list, and they asked 96 respondents to give them continuations for different partial sentences, like John apologized to Mary because. And they then used these responses to compute a bias score for each verb, which ranges from -100 for strongly object biasing to +100 for strongly subject biasing verbs. And in our case, we don't have 96 participants. We really want to be able to obtain such a score per model individually. So what we instead do is we say that this S subscript wins is going to be the number of stimuli for which the model referred back to the subject per verb. So for apologize, we have 200 stimuli, and S wins is going to be the number of out of these 200 when the model continued the sentence with a pronoun referring back to the subject. And here are the results in most abstract terms. In the human-based study carried out by Festo, about 52% of the verbs emerged as subject bias verbs and another 48 as object bias verbs. So the list of 305 verbs is, so to say, balanced between these two options. And what we see for the language models is that all of them tend towards object bias. And in the case of BERT and GPT-2, that's pretty extreme. And here is how the scores for the different verbs actually map between the human scores. Oh, I'm sorry that I'm missing labels for the axis here, but on the x-axis, we see the human scores for the 305 verbs. And on the y-axis, we see the model scores for these same verbs. And basically what you can see here is the same thing that we just saw, that GPT-2 and BERT basically land in the lower half of the graphs. Electra is better distributed. But even if you look at this lower half for BERT, for example, you can see that in the fourth quadrant, values do tend to be higher compared to the third one. So even though overall the models are leaning towards object bias, the strength of this object bias seems to be to some extent modulated by the implicit causality bias. And here is how we actually measure the correspondence between these two numbers in terms of Spearman correlation on one hand, where we see that for all three models, this correlation is significant. And it appears to be weaker for GPT-2, stronger for BERT, and strongest for Electra. And on the other hand, we measure their the correspondence in terms of F1 score over the polarity of the verbs. And this is basically asking if a verb is subject biasing according to humans, is it also subject biasing according to the model? And GPT-2 and BERT basically land pretty close to the baseline in this respect, whereas Electra shows a better awareness of where verbs should land in this respect. Okay, and then thinking back to the gender bias I mentioned and to the linear order bias, since we have now seen that the linear order, or whether you think of it as linear order actually, and say that the model has a recency bias, or whether you think of it as syntactic function and say that the model has an object bias, one way or another, it does seem to be the case that all these models on the whole prefer to refer back to the object of a sentence than to its subject. So here we try to discount for this effect because we're interested to know if we remove this effect, what is the real, what are we left with in terms of implicit causality bias effect? So what we find is that, oh, right. So the way we discount for the bias is by subtracting from the probability of a pronoun as obtained directly from the model, the average probability for that pronoun in any context that has that same schematic formulation as the actual stimulus we're looking at. And you don't really need to understand exactly what we did, because in practice it turns out that this doesn't have a very strong effect on the correlations, because in white here in the table we see the numbers I previously showed you, and in yellow we see the new numbers, and the Spearman rho doesn't really change for GPT-2 and Electra, and it becomes slightly higher for BERT. And obviously the F1 score goes up for GPT-2 and Electra because we've basically shifted all of their biases across the 0 point, basically. So we have forced them to acknowledge that some verbs are subject biasing as well. And lastly, one additional thing we did to make sure that whatever procedure we were using to get an output from the models was not, I don't know, giving us false signals or giving us incomplete information, is we looked at the correlation on the level of representations themselves. So we took the representation of a verb like apologize as the average over all contexts in which we've seen the verb. And we used latent discriminant analysis to identify one dimension in this representation that best correlates with implicit causality bias. And you can see that in the 1D row of the table. And you can see that basically for GPT-2 and BERT, we find a slightly stronger signal, and for Electra, a slightly weaker signal, which is to say something like, maybe by looking at the output of GPT-2 and BERT, we're not seeing the full extent of these models' awareness of IC bias, whereas for Electra, it might say something like, Electra's awareness of IC bias is encoded in a more distributed fashion than it is for the other two models. And we did something similar where we took 10% of the dimensions as well. And we trained a linear regression model. This was just to sort of try out different things, but at the end of the day, a lot of these results are quite similar. And a lot of them basically are saying these models have a certain level of awareness of implicit causality bias. So this is sort of our takeaway. On one side, they do seem to be aware of implicit causality bias. On the other side, their preference at inference time for a reference seems to be dominated by this recency or object bias, from which we could say that models, what models know and how they use it is not always the same thing. Because if we were to just look at the output of the models, we might not have, without looking at the correlations, we might not have become aware of their awareness of IC bias. Okay, we've established that there is some awareness of implicit causality bias. Now we're interested to know how that interacts with the model's ability to process explicit cues for causality. And in that respect, we use data from Garnham and colleagues 96, who compiled this list of 128 sentences, where each sentence goes something like, John apologized to Mary because blank felt offended. And the question is, what should go? Okay, actually, in their case, I should say, it said something like, John apologized to Mary because she felt offended. And then they asked participants, what does she refer to? But in our case, it's just easier to directly ask the model to fill in the blank. So that's what we do. And I put a little question here as to whether this amount of data is too little, because that's one of the points of criticism that reviewers had brought up. And in that respect, I think that this task is similar to something like the Vinograd Schema Challenge, which also contains fairly few data points. And the reason few data points are enough for these tasks is because humans don't make any mistakes on them. Because the Vinograd Schema Challenge, for example, was designed on the premise that if a machine, or like if the person being tested, the subject being tested, makes even 2 or 3 mistakes on these questions, we already should be able to conclude that this subject is a machine and not a human. And here we have a similar story where if the subject being tested makes more than what would be assumed to be a permissible accidental mistakes, so 2, 3, whatever, we can already say, okay, these models are not doing the integration of signals correctly. And here are the results from testing the 3 models on these kind of stimuli. So a little reminder, a congruent stimulus would be John annoyed Mary because he wouldn't stop talking. An incongruent one would be John annoyed Mary because she wasn't in the mood for jokes. And basically what we find, and bear in mind that because the data is balanced, the naive baseline is 50%, what we find is that all models outperform this baseline. But we also see an interesting pattern in what the gap is between the congruent examples and the incongruent ones. Such that for GPT-2, the gap is pretty small. For BERT, it's quite large. And for Electra, it's somewhere in between. And I think it makes sense to look at these results with reference back to what we saw in the first part of the study for the first research question, because it appears that GPT-2 having a fairly low awareness of implicit causality bias, or to put it more directly, showing a fairly low correlation with human scores on implicit causality bias, also suffers less from this interference effect. And that is why it shows this smaller gap between the congruent and incongruent samples. BERT shows both a stronger correlation to human scores in terms of implicit causality bias, and also a much larger gap. And then we have Electra, which sort of, let's say, breaks the pattern, because it has a strong correlation to human implicit causality bias, but it also has a smaller gap compared to BERT. So from this, one tentative conclusion could be Electra has a better awareness of implicit causality bias, but it is also a model better capable of integrating these implicit signals with the explicit cues that it gets from its context. So the takeaways from this part of the study are that all models show a gap in performance on coreference resolution between congruent and incongruent contexts. And the gap is not proportional to the model's awareness, in that Electra seems to be better at integrating the 2 signals. So basically, if we go back to our hypothesis, we can say that we do find some evidence in support of the idea that latency in human processing should translate into errors in model processing. And now the question is, so what, right? So one thing I want to mention, going back to what I said at the start, is that I don't think the main takeaway from this paper should be a matter of, I don't know, something like Electra is better, so we should use it for other NLP tasks. For one thing, because I don't think that comparing models on such a narrow aspect of linguistic processing can be extremely enlightening. Sure, if you take this paper and 10 other papers that look at 10 other narrow aspects, at the end of it, you might find that Electra tends to outperform other models on all of them. and draw some conclusions about whatever actual NLP tasks you want to solve. But I think that there's a bigger picture to see here, which is that because neural language models trip, as Alison Ettinger puts it, over contexts that require this kind of integration of multiple contradicting signals, it's not clear to me that whether more data or more parameters or longer training or whatever it is will solve this problem. Basically, there has been this debate in NLP for some time as to whether we are on the right path and whether gradual progression will take us to our goals. And kind of what we try to show by studying this hypothesis is that there is a certain mechanism in human processing that currently models don't manage to apply, or a certain ability that models don't show. So in that sense, it's not so much about whether, like, which of these three models is better, but it's just a matter of all three models, which are representative of three quite different approaches in NLP, show the same susceptibility to this challenging context. And therefore, the question should be, are these the right kind of models, I think? And I'd be very curious to hear your thoughts on that. Thank you very much.